introduction. Okay. Welcome, everybody. Thanks for coming. Today, we're very thrilled to have Sherry again. Sherry is an assistant professor of computer science at NYU Courant and a staff research scientist at Google DeepMind. She researches in machine learning with a focus on reinforcement learning and generative modeling. Her current research interest includes learning world models and agents and their applications in robotics and AI for science. Her research has been recognized by the Best Paper Award at ICLR and various media outlets such as VentureBeat and TWIML. She has organized tutorials, workshops, and served as area chairs at major conferences as well. Prior to her current role, she was a postdoc at Stanford working with Percy Liang, and she received her Ph.D. from UC Berkeley, advised by Pieter, Abbeel, and master and bachelor's degree from MIT. All right. So thanks again for coming, Sherry. The floor is all yours.
All right. Yeah, thank you for the introduction. And hi, everyone. I'm very excited to be here to tell you about this exciting line of work that we've been working on for like a few years now, but it started to become more emergent and started to build like a community around it. So today's talk is the title is Learning World Models and Physical Agents. And I think one of the things that we all agree on is that when we have some agents interacting with some environments, and we've sort of figured out a way to how to improve these agents to achieve superhuman performance. And specifically what we have is in the past where the environment, for example, is the Go board where the agent just places pieces and sort of have a way to figure out through reinforcement learning how to achieve, performance better than humans, for example. And another example for an agent backed by a neural network interacting with some environments. So yeah, this is to show you like when we have an access to an environment, right? Like the agent is able to really learn from interaction. Another example is perhaps more recent where the agent is empowered by these large language models and the environment is something like a terminal or some kind of execution environment. And what we've seen in this case is that the agent can interact with this environment and actually learn to, again, achieve superhuman performance on, achieving the gold medal from this ICPC programming contest. So it does seem like from these experiences, right, it seems like once we have high capacity enough of an agent, right, usually backed by neural networks, and some low cost environment, right? For example, the rolling out, playing keyboard, playing chess or Go is somewhat low cost because you can just place the pieces immediately. And also executing code is somewhat low cost because things are all just virtual. And with like also an accurate dynamics and reward, right? Because in a Go and also in program execution, all of these things are happening in real time. So exactly what happened, there is no difference between when the agent is learning through interaction versus when the agent is being tested. So yeah, so like, for example, we've already seen that these things are kind of true where we have, cheap, low cost environment like game simulations or program execution, and we have these large neural networks for these existing settings we've talked about, right? AlphaGo and LLM for coding or for math. But I think like a more intriguing question is not all of the environments have the property of being low cost, right? For example, when we talk about physical environments, especially with robots, the interaction is in no way low cost, right? The cost is both in terms of time and also in terms of money spent on buying robots and bottlenecked experiments being bottlenecked by robots. So in this talk, we're going to focus on because we know if we have like an efficient environment, a low cost environment, we can learn agents that are superhuman. So like the question is in environments where there is, when the environment is not low cost, what do we do? So in the first of the part of the talk, we're going to talk about how can we utilize data collected from these expensive environments to actually learn a simulator of the world, which is called a world model, so that we can actually have, cheap access to running policies, for example, in this simulator, so that we can easily evaluate policies. And on top of evaluating policies, we'll also talk about, once we have a learned cheap simulator of the world, how we can, apply various learning algorithms to improve the policies, such as reinforcement learning and various planning and search methods. Okay, so that being said, let's start looking at exactly how we're gonna learn a world model, right? By the way, like the video you're seeing here is actually not a real world video. It's a video that is generated from the world model, right? So we're gonna look at exactly how this model was learned. So actually, the background on world modeling actually has somewhat of a history, right? So in 2018, and there are a couple of papers that already started talking about world models. And even when, Jürgen Schmidhuber, probably from the last century, also had concepts of world models. And so the concept of a world model is actually pretty straightforward. So essentially, it is a dynamics model where the model takes in some observations, for example, the current or previous observations in frames of the current environment. And the world model is given some actions. And for example, control actions, right? In games, it's the keyboard controls, or in robots, it's the robot, pose controls or actions that are given to the robot. And what the model output is just basically what happens after this action is executed, which is just the next frames or the next few frames if the actions are, spanning a few frames long. So this is the definition of a world model. But then the question is like, if the concept of world model has existed for a while, then what is different now, right? Why is all of a sudden world modeling becoming like an interesting topic? And I think there are a couple of things that makes world modeling interesting for the current moment. One being that internet scale video data becoming available for learning world models, right? If you look at these previous work, because learning world model is somewhat sample inefficient, you need a lot of data to capture all kinds of possibilities and counterfactuals of what happens if I do this. So in the past, people mostly learn world models in game settings where you can draw just infinite samples from games. But now, right, we have like a much richer data set, a large scale data set, so we're not only confining games anymore. And on top of these large-scale data sets becoming available, there is also this scalable video generation architectures backed by transformers that really revolutionize the language learning, but also now I think for embodied learning and for world models is also something that is very special to the current time. So with that being said, I want to show you some examples of exactly, how to utilize these internet data and these scalable video architectures. So this is the work that was published at ICLR 2024. And the main takeaway from this work is that there's actually very rich information from internet scale video data, right? And specifically, what kind of information is in these data sets? Well, for example, the dataset actually already contain information on how to perform certain tasks, right? So for example, if you condition on the first frame of a human in the kitchen, an egocentric image, and if the world model can predict future frames conditioned on some actions such as, this text action, cutting peppers, then during generating this video from this world model on reacting to this action of cutting peppers, the model actually learned how exactly is this task performed, right? So in some sense, we're repurposing a video generation model, a conditional video generation model, as a world model by giving it some initial frame and some actions to generate the effect of executing these actions. And just to be clear, like the actions here can be very broad, right? It can be text-based actions describing the activity. It could also be very low level fine-grained control actions for robots, right? In this case, the controls are, delta X, delta Y of how to move the robot endpoint. And if the model can faithfully predict the next frame as a result of executing these actions, in some sense, the model has implicitly captured some physics, right, in order to be able to predict the next frame accurately. And not just that, we can model real robot videos. We can also model simulated robot data sets, right? And using the same model, still the same model, same modeling objective. It's just the data set that's different. And in this case, the observation is that usually there's diverse data set from the internet, but each part of the data actually captures different kind of information, right? From this data, we have maybe diverse activities from humans, but there is no robot motions and there is no low-level actions. And some other data has like low-level actions and robots, but maybe they're not as diverse, right? And then there is also data that's, we can curate infinite amount of data from simulators, but maybe the physical realism is lacking and the rendering of the observations is not realistic, right? So it seems like each of these data have some characteristics that all of this information should come together somehow to be able to enable a really powerful world model. So this is actually, what we can achieve through this conditional generative modeling, right? And again, using the same model, we can really model different types of data with different types of information. In this case, if you have some egocentric motions and you have some actions as camera controls, like turning left, turning right, you can condition on this camera information action to predict the future frame. And then again, like the model had learned some sort of egocentric motion. So yeah, so basically in this work from 2024, what we did was we just gathered a bunch of data from the internet. So these data include things like simulated data from Habitat, for example. It includes also data from real robots. At the time, there was no this data called OpenX embodiment yet, so we had to like collect each of these robotics data individually. But nevertheless, right, we can curate this data set because we have a common modeling objective, which is this conditional video generation. And all we need is just gather as much data as possible. And there's also data from humans like U4D and various egocentric data set as well. And that's on the data side, right? Like I said, what's special about doing world modeling at the current moment is the access to internet data and then also scalable video generation architectures, right? So in this particular case, the architecture we chose and also later on, like consecutive work started to use is this latent diffusion transformer style of architecture where the images are embedded into some latent space, and we have an autoregressive transformer that predicts these image latents and using diffusion models to refine these latents before they're decoded back to the real observations, right? So, and we've observed that this architecture is able to really absorb these broad data sets and as a result, show some generalization. So I guess we've talked so much about, what the real world, like the world model is built, but maybe just to give you some example. And I think it's better if you can just like open up your browser and go to the website that is, it's not showing, but like universalsimulator.github.io. And you can see some examples of these are cached, right? These are pre-generated videos, but I will show you another example where, the videos is actually generating on the fly later in the talk. But in this example, what you can do is you can really choose from a diverse initial frames. And then by choosing a scene, right, you could then specify the language instruction you would like to give to the model. For example, you can ask the person to wash hands, and you can have follow-up actions like after they wash hands, ask them to shut off water, right? And really you can, starting from the initial frame, you can have very diverse actions. And this is the point of a world model. It's not just video generation. It's controllable video generation with all of these counterfactuals. What happens if I ask the person to cut carrots? What happens if I ask the person to wash hands? And even what happens if I ask the person to turn left, right? You see like the person actually turned away from the kitchen and walked into a dining room. So all of these videos are generated, and it's not even clear, like we cannot backtrace exactly whether there was a dining room right in this video because the model was really composing these concepts of dining rooms and kitchens after we have these language instruction. And similarly, you can sort of really use language to create this virtual world, right? About what happens if some actions are executed. You can specify the world will reveal a toothpaste if someone to uncover this napkin. And you can really specify any kind of objects, right? So this is really showing you how you can curate this virtual world. I mean, we'll talk about how this curated virtual world will be used in later parts of the talk, but at least this is showing you, what's possible once you train this model. And you can really specify, you can ask a person to put an apple on the plate. You can ask a person to, not put an apple, but instead push the plates away. So it's really sort of reacting to these action-based inputs, right? And now, like also just controlling humans is the same as controlling robots in this world model. We'll just give it some language instructions or low-level controls, which we will show again later in the talk. But here, there are some examples of we try to control the robot with, at least virtually, right, in the world model with this language where we ask the model to put sponge in the drawer or like close bottom drawer. After the model closes the bottom drawer, it needs to start from the previous frame of the drawer being closed to reopen the drawer if we specify this, right, and open the top drawer. You see, like, because the bottom drawer was closed, so when we, specify the second action of opening the top drawer, like the bottom drawer is staying closed. So again, like this is the same model where you can do, manipulation or navigation of in different initial frames. So,
Yes.
okay,
I'm going to ask a quick question, Sherry.
sure, go for it.
I guess great. So then also on more so in the context for robotics. And you mentioned a couple of examples of robotics data sets that have, some good quality data here and there. But where do you think we're still lacking data, maybe more so in the robotics context, to really fill in some of the spaces that may be left in models like these?
Yeah, so I think in general, these models are okay. I think it depends on what kind of generalization are we expecting. I think currently these models are reasonable in terms of generalizing to, say, new language instructions, right? So in the particular training example, in this particular frame, like there was only one particular task that was performed, but now we can give it different language instructions and the model can react to different language instructions. But I think the generalization to an arbitrary robot in an arbitrary environment is still lacking. And I think that is due to a very narrow distribution of the robot data set, right? Even if you look at like the largest robotics data set we have now, which is like OpenX embodiment, it has, maybe just a dozen robots. And also like most of the robots are of very low quantity data. Only like maybe this Google robot and the bridge robot had like more data. And so I would say like the settings of different robots is lacking. And in some sense, like for example, the reason I think text has made so much progress or language model has made so much progress is that all of the text data that we consume or produce is uploaded onto the internet. Whereas for robotics, I have a robot lab as well. Like none of my data is being streamed to the internet, right? It's saved on some server running my robots. So I think if we can figure out a way to, have a shared data hub, and share all of the robots, because it's not like we're not running enough robots. There are so many robotic labs. There's so much data being recorded. It's just that we don't have a common channel for sharing these data. I hope that answers your question. So
Yeah, it makes sense. Thank you.
yeah. Yeah. Okay. Yeah, I mean, despite that data challenge, right, I do want to talk a little bit about like, some current ways of using the world model. There are still very promising aspects of using the world model for robotics. I think how to streamline the data to scale up the data, I think is something for the future work, but nevertheless, there is already exciting science of life. Before that, I just want to summarize some major takeaways from world modeling. I think the concept of next frame action condition, next frame prediction existed for a long time, but it's only becoming exciting when we have diverse data from the internet, data from humans, data with different control information now all coming together, so we can have a world model where we can control it using different levels of abstraction for the actions, right? We can use text actions, which are pretty abstract and like long in the time horizon, and we can also have very specific controls. So these information, I think this diverse information is one aspect of world modeling that's exciting. And so, right, so, after we've learned this model, I think maybe it becomes natural of asking ourselves, like, how are we going to use the world model? Because I think there are so many people are working on world models now, but like, it's not super clear how are they useful, right? And the reason we want to really investigate on the application or the usefulness is because that will define our evaluation metric, that will define, ways to improve, right? Because if we just have some cooked up video generation metrics for evaluating world models, that's just not how we're going to iterate. Only through usage would we discover new issues, right? So, and the concrete usage I want to talk about today is using a world model to evaluate policies. And there is very much motivations for that, right? Just to give you some example of why we want to evaluate policies in the world model. This is because like real world evaluation is just expensive, right? They're expensive in various aspects. Like it takes time to run real world trials. And oftentimes if you want to make sure like your results are robust, you should run your same task like 10 times and compute, or even 100 times and compute the success rate, right? And that's just, if you have one robot arm, that's just gonna take a long time. And if you want to test this in diverse tasks or diverse initial conditions, initial frames, that's just gonna take forever. So not just the time cost, but the safety cost, right? If your policy is not perfect, it just smashes the hand into the table, and now you have to wait for a month for the new robot arm to arrive, to be assembled. That's just very expensive. And another aspect of difficulty of real real world evaluation is reproducibility, right? Each lab has its own setup for the robots and different lighting conditions and so on. So one of the issues I think that maybe robotics has evolved so slowly as a community is because it's very hard to utilize work from other groups just because the evaluation settings are all different. We all use different robots, or even if we use the same robot, the settings are different. So I think that reproducibility issue is real, right? Because we can't really just directly compare two policies easily that are developed by two different labs because the initial frames from two different labs are just different. So okay, so this is challenges of real world evaluation. So what people have done in the past is instead of doing real world evaluation, let's just use simulators to evaluate policies. But then there are also questions because the gap from sim to real, especially for image-based manipulation, is just so large that people just, end up training two policies, one for sim and they report the results in sim, and then they train another policy on real and report the results in real. But then again, that makes simulated evaluation almost useless for reflecting real world task success, right? Because simulators, not just the visuals are different from what the real world looks like, but also it's hard to simulate some physics, especially around like soft object interactions and so on. So, okay, there are various issues about simulated evaluation, especially in like the low correlation with real world task success. So, we've looked at this world model, right, that we can train using, future frame action condition, future frame prediction. So maybe the proposal we're going to use here is to, take all of these robot data, and specifically if we're talking about evaluating policies, right, then the input to the world model should be the output of the policy, which is just these low-level controls, right, these action vectors. So in this more recent work called World Gym, what we did is basically we take this OpenX embodiment data set, which has 22 different embodiments of robots and very, very diverse settings. And we use the same architecture we described earlier to condition on a sequence of control actions to predict a sequence of future frames. And as a test, right, an initial test we did is like after we train this model, we want to see if we can control the robot arms in some simple ways, right? So this is show you some example of what if we just move the robot along some particular action dimension, right? So the top two is what if we just move the robot left and right, up and down, or into and out of the page, or what happens if we just close and open the gripper, right? And we can do the same for different robots. We can do the same for this bridge robot. We can also do this for the Google robot, right? But remember the model is trained on like a single model is trained across these data sets, so we can actually use the model to control or to use the use different input the same control actions like left and right into different robots, starting from the different initial frame of different robots, and see like they're actually obeying these actions of moving left and right, right? And like to further give you an example, you can go to this another website, which is worldmodel-eval.github.io, and we actually have like a okay, sorry, I think that the server might be busy. Someone might be using it. But anyway, you can visit this website a little later. So the point being like I'm sorry, like I can't really do this demo. It's actually pretty cool, but you can, if I have time after the talk, I'll pull up the server to run it on my device directly. But the point being like you can actually use your keyboard to move the robot gripper to like different locations, left and right, up and down, and see if you can, pick up a banana, for example. So yeah, sorry, I can't do the demo right now. I will try to do it later. And then after we've tested, like we can, like it seems like the world model is roughly obeying these control actions. What we can do is we can try to run some policies, right? Remember, we have this issue of comparing different policies is just hard because you can't really run them in the real world when you have different lab settings. And now, despite these three policies, Octo, OpenVLA, and RT1, were developed by 3 different institutions, right? But now once we have this world model, we can actually roll out the policy in this world model virtually, right? And what happens is like the policy will take the initial frame and it will predict the sequence of actions, and we will execute those sequence of actions by predicting the next set of frames in the world model. And then we give the last frame back to the policy for the policy to roll out the next set of actions, right? So this is what the rollout process looks like. It's actually iterative. The policy will interact with the world model multiple times as if it's executing actions in the real world. And then in return, we will get a sequence of frames, right? The generated video conditioned on the actions outputted by the policy. And then we can use a large language model, vision language model as a reward model to tell us, was this a success, right? And these are tasks, are language condition tasks. So we know what should happen if the task is to, to pick up the pot. And then we can give the generated video to VLM to ask whether the task was successful. So to show you some examples, right? So this is when we ran these 3 policies in this world model. And in the first example, you can see that this is what happens in OpenVLA when we try to, so this is the task inputted to the policy, right? Put eggplant into pot. And this is what OpenVLA's rollout looks like in the world model. It looks, pretty reasonable. And then, we did the same thing for Octo. And we see that, okay, Octo seems to struggle a little bit, but at least it's trying to pick up the eggplant, right? It's in the right direction. And then when we did RT1, which is like a model that was developed a couple of years ago, that's older than the other 2 policies, and we see that the policy wasn't really doing things that are reasonable. So, and the actions were so sort of off that even the world model started to hallucinate a bit. But nevertheless, it's still pretty easy for the vision language model to observe these videos and to tell us, OpenVLA's rollout is successful, whereas Octo and RT1 is struggling. So this is really something that's very hard to do, right? In the past, like whenever you read like a new robot policy came out from some lab, like you just have to trust the numbers from their paper. But now you can actually, train their policy on OpenX embodiment and roll out their policy in this world model and see how exactly their policy actually does. So, and this is some examples of, you can not just roll out this for the same, you can also test their policies in different settings, right? When they try to train generalist policies that can control any embodiment. So this is an example of controlling like the Google robots. And it seems like the task is simple enough for all 3 policies to be able to successfully complete the task, which is to close the bottom drawer. So this is some qualitative examples. And so quantitatively, we actually, follow the exact evaluation settings of OpenVLA, where we run 10 trials per initial frame per task, right? And then we measure the success rate in the world model and compare that to the success rate of executing the policy in the real world, right? And we actually got the initial frame of the evaluation set from the authors of OpenVLA, and we just input this initial frame into the world model and start to roll out the policies like that. And you can see that the success rate for what happens in the real world versus what happened in the world model is actually, close enough for the world model to be useful, right? So maybe the difference is around 2-3% for these 3 policies we looked at. And then the order of the policies, right? Like RT1X performed the worst, followed by Octo, and followed by OpenVLA, which performed significantly better than the other 2 policies. This is true for both real world evaluation and for the numbers we got from the world model. And so I think these 3 policies, RT1X, Octo, and OpenVLA, they all used the same evaluation setting from Bridge, right? So this is where we got the initial frame from. But then there are also maybe policies that, okay, so on the left, we're just looking at comparing, different versions of the policies at different sizes to see if their performance according to the world model is roughly what we would expect, right? And then we took the smaller version of Octo, which is Octo small 1.5, and then Octo base, and we did find small underperforms base. And then we also took different versions of OpenVLA. This is an earlier version of OpenVLA, and this is a later version. We'll also see that the later version outperformed the earlier version. There are also other policies, for example, this universal policy UniPy of generating videos and doing inverse dynamics to get the actions. And then there is also diffusion policies, which just predicts the future actions conditioned on the frame using a diffusion model. These policies didn't really train on OpenX embodiment, so it's a little. So they didn't evaluate on OpenX embodiment. They didn't evaluate on Bridge, so they don't have a real task success. So we couldn't get some plots like this. But nevertheless, we could still look at, we just take their policy code and we train the policy on the OpenX embodiment data, and we observe what happens to the accuracy when we evaluate the policy across different training stages, right? So across different checkpoints, we see that both the video policy and the diffusion policy improves in accuracy across training. So this is again verifying that the world model is actually reflecting even the training stages of how the policies are performing across different time steps, across different training steps.
Can you hear me okay, Carrie?
Yeah, I can hear you.
Sorry. So can you just remind me and give me some details on how you measure success from the world model? Like, are people watching their videos and marking them, or how does that work?
Yeah, so it's actually using a vision language model. So of course, we also have human evaluations of the vision language model in the appendix of this paper, World Gym. But in general, what we found is that the vision language model is actually pretty good in terms of agreeing with humans of whether the task is successful or not. Because usually these tasks have a task description, right? For example, put eggplant into pot. And then we ask, this is the rollout video, and we ask the vision language model, was this successful? In terms of completing the task. And I think one thing is that, we can get the 0-1 binary success from the vision language model, but we can also get more of a, when both policies fail to complete the task, for example, maybe Octo and RT1, and we can still get some more information from the world model in terms of which one made further progress, right? Just by, if we ask the vision language model to assign, say, partial credits, right? In this case, the Octo will get partial credits because it does seem to pick up the eggplant, whereas the Google RT1 policy is just completely not doing the right thing. So in short, we use a vision language model to automate the process of computing the reward. And on top of that, I think VLM will be pretty useful in terms of assigning partial credits, or even providing some kind of useful debugging tools to give us an idea of where the policy is failing. Does that answer your question?
Yeah, thank you.
Okay, cool. Okay, so this is just some kind of verification of whether the world model is reflecting, maybe real world successes. I think there is something that's very intriguing, about using the world model. And I think this is something that's very difficult to do in the real world or in a simulator, software-based simulator, which is this flexibility of testing from an arbitrary initial frame, right? But with the world model, what we can do is we can use these image editing tools, for example, this Nano Banana from Google. And in this particular example, what we did is that we used Nano Banana to edit the image to add an additional object, which is an orange. And then we ask the policy, right? Because the policy is a vision language policy. It's supposed to generalize to new task instructions. And we added this image and we give the policy the new language instruction, asking the policy to pick up the orange. But what we found is that all of the policy just fails, right? All of the policies just, overfitting to this task of picking up the carrot, as opposed to generalizing to picking up this new orange. We've also did something that's quite funny, which is we put this computer screen, because this is just trying to show you that with Nano Banana we can really create any kind of adversarial settings, or that we can test how would the policy react in these settings. And in this case, we put a computer screen in this kitchen environment and ask the policy to pick up the carrots. And what happens is that you can see the policy actually really is debating, right? Which one should I go? So it's swing back and forth, and eventually it tries to pick up the banana from the computer screen, which, is not what it's supposed to do. Of course, it does seem like even the carrot from the computer screen started to move a bit. So that's kind of failures of the world model, but nevertheless, it's already showing you what's possible with image editing plus world models. And so in addition to just now we can really use the world model to test various axes about the policy to diagnose, is the policy bad with color? Is the policy bad with shape? And does the policy preserve internet scale knowledge about, Taylor Swift or Snoop Dogg? So this is some example where we edited the image, again, using Nano Banana to place, different colored rags on the counter, for example, the blue and the red. We also, have the same color but different shapes, square and circle, or we place, different posters of different celebrities, and we ask the policy to pick the right, color or shape, for example, pick up red. And what we found is that the policy, especially OpenVLA, we mostly did experiments with OpenVLA because it's the most reliable policy among all. And we found the policy is pretty good with color, Specifically, when we say pick red, it always moves to the red direction. When we say pick blue, it always moves to the blue direction. The success rate is pretty high. But we found the policy is very bad with shapes. Like when we say pick circle, it's almost arbitrary random chance which shape the policy will pick. And I think one of the reasons is our hypothesis is that these visual language, OpenVLA, for example, these visual language action models, they're fine-tuned from VLMs. And then during fine-tuning, oftentimes the task specification has some color information. For example, like pick up the yellow banana, right? And that's more common than the task description containing things about the shape, like pick up the long banana, which is very rare to see. Whereas the color, pick up the red X or pick up the red potato or something, a tomato. So that's like quite common in the task description. So that's one of the hypotheses of why the policy is pretty bad with shapes, but okay with colors. And then as for preserving internet scale knowledge, we found the VLA policies to generally fail pretty miserably. In this case, we try to ask the policy to pick Taylor Swift, but again, it's pretty random chance of where the policy would move in this case. And I think this is something to think about going forward because everyone now is thinking about fine-tuning VLMs into VLAs and hoping they will just arbitrarily generalize to any task. And I think like this is a really good example telling us like the internet scale knowledge was actually lost during the fine-tuning process of the VLM, right? Because if you were to ask a visual language model, which one is Taylor Swift, left and right, Taylor Swift versus Snoop Dogg, I think you can pretty much, get correct answers. And which means that the visual language model actually have these information, but during the fine-tuning process, because we're supervising the model on the very narrow distribution of the task for which we have collected data, right? And then, the model just is not able to preserve information about, internet knowledge like celebrities. So I think that's something to think about if we're all gonna focus on, fine-tuning VLMs into VLAs. Okay, so those are some settings where we were thinking about, testing different axes of the policy. And now we can think about, in general, maybe one most desirable property of a policy we want is for the policy to be robust, right? To not be distracted by arbitrary objects. And in this case, we can, again, use the image editing tool, Nano Banana, to add some distractors. In this case, we added this rubber duck and this toy truck. And what we did is, we again asked the policy to perform the task, which is to pick up this pot. And we found that with these distractors, the accuracy or success rate according to the world model has dropped significantly across all of these policies, right? Like they've dropped by more than half in terms of accuracy. So it's telling us that, the policies are not really robust against these distractor objects. But it also opens up like future venues of research, which is, okay, now we have this simulator where we can train the policy, right, to become more robust against these distractor objects, and those are considered future work. Okay, so maybe to revisit where we came from about using world model for policy evaluation, right? We talked about how they're very expensive to run real world evaluations. And now with a world model, right? Like in the past, if you have to, execute the real robot across many tasks, across many trials, it's just, a student will have to wait there for a very long time. But now in the world model, the entire evaluation suite runs in under 1 GPU hour, right? And again, like you can avoid hardware failures and you can execute multiple virtual trials in parallel. And more importantly, you can really compare different policies that are developed by different labs. And of course, there's still kind of like more work to do. Like you've already seen some hallucinations. For example, when the policy was trying to pick the carrot from the computer screen, it seems like the carrot even moved a little bit, right? So this is, future work. And I think like scaling up data is definitely one axis we should be looking at to reduce these hallucinations. But nevertheless, right, I think these out of distribution tests that we did with, distractors or with different colors and shapes, I think those are really very intriguing properties about using world models to evaluate policies that, was never able to be achieved in real world evaluation or in software simulators. Okay, so, right, so to recap, right, so, we want to use the world model to evaluate policies because they're cheap, they're safe, they're reproducible, and they're flexible for testing OOD scenarios. And of course, there's more work to do to make the world model more realistic, but I think we're still to the point that the world model is already useful for running evaluations. And my lab is actually using world models before we try to run any real robot experiments. Okay, before we move on to the third part of the talk, are there any questions? Okay. All right. So now, so we've talked about policy evaluation, right? And maybe let's now just spend some time thinking about how are we going to use the world model to run RL and planning for improving the world model, or for improving the policy. So the concept is pretty simple, right? So remember, we have this pipeline where we roll out the policy in the world model. We use the VLM as reward. We get the success and failures from the VLM. And now actually using this information to improve the policy is fairly straightforward, where you can, apply policy gradient using this reward information from the VLM and to update the weight of the policy, right? And we actually did something like this. This is still like the work from this 2024 ICLR paper, where at the time we're using this PaLM policy, which is the PaLM model fine-tuned from Google, fine-tuned on some robot data. And if you do this directly in the simulator, if you run RL in the simulator, right, you really don't get transfer, even for this very simple task, which is to rearrange the blocks on the table according to some language instruction, right? Because the simulator and the real world just look so different, even for this very simple task. And instead, what we did is we trained a world model, action condition future frame prediction model, and now we can roll out the policy, in many different tasks simultaneously using this world model. And what you're seeing on the right is the generated frames from executing this policy in the world model. And then because this world model is learned on real world data and looks very much like the real world, the policy was actually able to generalize zero shot to the real world performing this new task, which is to push the red star towards the blue cube. So you can see that this is real world execution. So I think the answer maybe to the longstanding question of sim to real transfer might just be to have a very realistic simulator learn from real world data. And this is to show you some results on what happens when we use the world model to run RL versus if we just use the data collected for training the world model to only run behavioral cloning. And we saw that the success rates from running RL actually improves dramatically compared to if we only run BC. Because if we only run BC, there is no way for us to utilize failure data. Whereas if we use the world model, it could benefit from failure data to learn the dynamics, and we can use these dynamics to improve the policies. So this is the task where it's pretty straightforward in terms of language. It's just some kind of movement, so we can actually train a low-level control policy to move the blocks. But if we have some tasks that are more sort of long horizon, and for example, we want to control the robot to put all of the objects into the top drawer, right? So this is a pretty long horizon task where the robot has to open the top drawer, put one object and put another object. So in this case, it's more difficult to just directly run RL because of the long horizon and sparse reward issues. So instead, what we do, because remember, our world model can take language instruction, right? So instead, what we can do is we can ask the world model to first generate, condition on this text of putting the fruits in the top drawer, to generate this video that corresponds to what we would want, which is open the top drawer, put one fruit, put another fruit. You see that the video is generated because the banana actually changed shapes, but nevertheless, it didn't really matter for the control purposes where we generate this video. So this idea is from this universal simulator. This learning universal policies through a text-guided video generation idea called UniPy. And you can convert the generated video into low-level robot controls by training a separate inverse dynamics. And on the right is, after we recover the inverse dynamics from the generated video, this is the execution on the real robot, right? So this is showing you the execution on the real robot is very similar to how the robot has imagined itself executing this task. And I think one of the things I wanted to talk about is like, why do we want to do planning, right? Why do we want to generate videos and then extract action? And the reason being, if you think about what happens in behavioral cloning, when you're supervising from image observation to the low-level controls with the policy pi, this is the setting of behavioral cloning. And the difficulty of this is that you have, different robots with different actions spaces, and there's just no knowledge sharing, right, across different robots. And you can try to train a single policy, but then the action spaces are different, so it's not clear how much transfer you would actually get. But if you instead train a world model and then train text condition video generation to do planning in this world model, then all of this information, right, across different morphologies and across different tasks basically turns into learning to control a set of pixels, right, using this shared policy. So you actually get a lot of knowledge sharing across different morphologies. And of course, you still need to convert the video into some robot controls. And different work have explored different ways to do this conversion, for example, using flow models or using a goal condition policy or using inverse dynamics like in UniPy. But nevertheless, maybe the exact low-level kinematics for different robots is different, but the high-level policy is now shared and can benefit from diverse data sets. And usually the scale of parameters is very different. For the video generation model, we have shared knowledge, shared data. It's of much larger parameters, whereas the inverse kinematics is much simpler because if you can model a movement very accurately in the image space, minus some partial observability, you should be able to recover the underlying kinematics relatively easily. Okay, so in order to actually generate this video, right, this is pretty long horizon. Like you can see there are multiple steps. For example, opening drawer, putting one fruit, putting another fruit. So it's actually not trivial to generate this video. If you just condition on put the fruit into the top drawer, it's kind of hard to generate this long horizon video. So what we actually ended up doing is called vision language planning in this particular work. So again, like the world model can do rollouts, right? So what we did is we can condition on the initial frame and ask the vision language model, what should we do as a first step if the goal is to put the fruits in the top drawer, right? And then the language model actually proposed something reasonable, like open the top drawer and maybe another sample, which is, place banana in the top drawer, which is not good because the top drawer is now open. But nevertheless, we can, generate these rollouts according to these actions in the world model. And we see that in one of the actions, the first step was successfully completed, which is opening the top drawer. Whereas the other one, it was not successful because the top drawer was not open. So we can't really generate a video of placing banana in the top drawer. So, and then it's pretty clear the top branch is the good branch. So we use the vision language model to select the correct branch. And then condition on the last frame of that, we can continue to roll out with a vision language action model for what happens next. Yeah, sorry, there's a missing slides here. But so what we do is we can take the last frame, we can ask the vision language model again, what's the next step, and then get the next action, and then get the next video, and so on and so forth, until we have a tree. And then we can really, in this simulated world model, we can select the branch that is actually successful in terms of completing this task. Right, so this is to show you some examples of completing this task of rearranging the blocks into a line. And you can see this is the language instruction that was, generated by the VLM. And then these are the videos generated by the world model for executing each of these language instructions. And then this is what happens, so this is generated frames, but these are the real world executions when we, convert the generated frames into low-level robot controls using an inverse dynamics model. And what we found is that with the world model, you can really scale up inference. You can, just generate multiple language instructions. And for each language instruction, you generate multiple videos and you use the VLM to select the good rollouts, right? And what we found is that the more language we generate per initial frame, and then the more videos we generate per language, the higher we actually achieve in terms of task success. So I think this is one of the ways to really, applying the Pieter lesson to robotics or in body settings to, use compute to search for the best plan in the world model for executing a real world task. Okay, so I think there are more justifications for why are we doing language and video-based planning, right? If you think about what people are doing with behavioral cloning, they're going from initial frame to a set of actions. And this mapping is too hard, right? It's pretty difficult to generalize, and you just need like a lot of data. And then what we saw is that, this behavioral cloning basically achieves almost nothing in terms of completion for this very difficult task of making a line, right? It's just too long horizon for BC to generalize. And then what happens with these video-based policies is that we can predict a set of frames that sort of as some kind of an anchor point, right? To, okay, what should the final stage look like if we rearrange the lines, right? And that really narrows down the actions that we need to learn in order to achieve this goal, right? So this goal-conditioned future frame generation followed by these action extraction. And then when we introduce, the hierarchical planning where we actually predict the language first and then predict the video for this language, we're almost adding another layer of abstraction for breaking down this task into steps and then for predicting the goal for each of the sub-steps before predicting these low-level control actions. And this makes sense mostly because, we're breaking down this very complex task of making a line with all of these blocks into something that's step by step, right? And then furthermore, for both the language coming up with the next language instruction and then condition on the language instruction to predict the video or predicting the goal, we actually have the internet scale supervision because we're working with language and video data, right? And this is why we're breaking down this task into very simple steps. And then especially for these high level difficult steps, we actually have internet supervision. Okay, so that is the last part of the talk where this is how we can do both reinforcement learning in the world model, where the input to the world model is low-level control actions. We can optimize those low-level controls directly, or we can actually condition on language in the world model to do these long horizon planning to get these future frames and then turning these future frames into actions through an inverse kinematics model. So I think this is showing us like how we can, combine knowledge across diverse environments because we have a single world model trained from all of the environments. And then more importantly, you can use, you can plan or search or do RL even at different temporal and abstraction levels using language, right? We've shown how we can, learn to perform a sub-step of completing a very complex task because the world model can handle actions of different levels of abstraction like text and low-level controls. So yeah, with that, I think I just want to conclude on some final thoughts where we started with this dream where, if we have a efficient universal environments, we basically, have developed the tools like RL, like planning to achieve superhuman performance. But I think the reason that we're not there for robotics is because we don't have access to this cheap environments, this simulators. And the key is really now in the world modeling, in developing a very efficient environment for robots and agents, physical agents to learn from, right? And then when we talk about learning world models, I think we must have to think about the usage about world models, which is, in evaluation or in training agents, because through the usage, would we actually get this data flywheel of from usage to more data and from more data to better models. And maybe the last a bit of thought is that today's world model is not perfect. And also there is, we can't really model any arbitrary high resolution videos at arbitrary precision, right? So there will be a point where we have to think about fidelity. So like at what, because, you can record a video at very high frames per second. And does that mean we need to model all of those high frequency, videos? And you can also record videos at very high resolution. But then the question is, at what temporal and spatial resolution do we actually need for a world model to be useful for downstream tasks, right? And so far, these decisions are pretty arbitrary. And, we model things at one frames per second, for example, or we choose a resolution at 512 by 512. But all of these should somewhat be task dependent or have some kind of notion of how this world model will be used eventually. And of course, given an imperfect dynamics and reward model, we've already shown like we can, they're already reflecting task successes for evaluating policies. So thinking about, because there are things that will be imperfect about world models, but would that necessarily have to affect the usage of the world model, like evaluation or like using the world model to improve policies? Those are the things to maybe spend more time on. If we have an imperfect world model, how can we, utilize the world model regardless, right? If they're already accurate in terms of modeling, like at least the rigid body movement. So yeah, with that, thank you for your attention. I just wanted to thank all of my collaborators across many different institutions and also across industry and academia. And I'm ready for any questions you might have.
Thanks a lot, Sherry. First from the people around, does anybody have a question? Go over it.
Hello, can you hear me?
Yeah.
Yeah, I have a question about, so in your world models, you showed that policies like RT1 and Octo are biased by the data. Like you showed the example of like the carrot and the orange, and the models would maybe always grab the carrot. And because they're not listening to the language due to maybe bias in data, like in that scene, it's always grabbing the carrot. Did you see similar things with the world models where they're also biased by data and they become less controllable in certain scenes? Like even you're telling the model to move to the left, but because in this scene, the data, it's always showing the gripper grabbing the carrot. So it's always just moving towards the carrot.
Yeah, so I mean, I've definitely seen maybe the bias is shown in a different way, where like the language instruction is a bit out of, or like the action is a little bit of out of distribution for the world model. The specific example is like the specific example is when the world model is not capturing some initial frame. Like for example, you don't see a robot arm in the world model, and then all of a sudden you say, move the arm to the left, right? So like this kind of things is when the world model is kind of caught a bit off guard. But I do want to make a point about the difference between the policy and the world model and their level of generalization. So I think the reason that it's more common for the policy to overfit is because they're trained specifically for the task. And in this initial frame, right? And then, it's just by looking at this frame, and people have found this also, like oftentimes you don't need the language instruction. Just by the initial frame, the policy already knows what to do in this case. And then you just need so many tasks to be able to, for the policy to generalize. But when you have like a world model, you can absorb data from diverse tasks, right? Even from tasks not from this particular policy. Like for example, to train the Octo policy, like people have to collect task-specific data. Whereas for world model, you can use internet scale data for, carrots and oranges. So I think the maybe the short answer is that people are training one policy, like task-specific policies in different scenarios, but we can use all of the data across policies to train a single world model that as a result can achieve better generalization than policies. That's my take on this. Yeah.
Thank you.
So we'll have to cut it short because there is a class in the room we're at. Hopefully people could they maybe email you the question, Sherry? Would that be possible? I'm really sorry about that.
Yeah, sorry, the talk was a little too long. I'll make sure.
No, it was perfect. But either way, I guess we'll leave it there. Again, thank you very much for giving the talk. It was very inspiring. But yeah, let's keep in touch. All right.
Okay, thank you.
All right. Thank you. Take care.